In other news, NASA's James Webb telescope has been making headlines for the images that it has brought us of our early universe.
They've just found a galaxy so old and massive, it shouldn't even exist. And it's forcing scientists to rewrite the very origin story of our universe.
You held a grain of sand on the tip of your finger at arm's length.
According to me, this changes everything. The James Webb Space Telescope has spotted impossibly huge galaxies only 500 million years after the Big Bang. And trust me, it's not supposed to happen. And here's where it gets even stranger. Renowned American physicist Michio Kaku saw this coming. At least the part where the James Webb Space Telescope would shake up everything we thought we knew. A year ago, he warned, we may have to rewrite all the textbooks about the beginning of the universe. And now JWST has delivered exactly that shock.
All right, we get these images of galaxies and all that over the years, the Hubble telescope, others, astronauts when they're circling the Earth or from the moon.
Problem? We used to believe it takes billions of years to form a galaxy like the Milky Way, with its 100 billion stars. But JWST has spotted 6 galaxies that existed just 500 million years after the Big Bang, and some of them are up to 10 times larger than the Milky Way. That shouldn't be possible. The early universe was supposed to be small, chaotic, and slow to build structure. Yet here we are, staring at cosmic giants that seem to have skipped billions of years of growth. So what went wrong with our theories? Either galaxies form much faster than we imagined, or there's something about the early universe we completely misunderstood. What do you think? Are we missing a piece of the puzzle, or the whole puzzle itself? Just when it seemed like the surprises were over, JWST pushed even further, peering back into the first 500 million years after the Big Bang. And instead of seeing young, faint galaxies barely forming, astronomers saw mature, massive galaxies that looked nothing like the fragile baby universes they expected. These weren't just bigger than they should be, they were fully developed, with structure, mass, and complexity way ahead of schedule. Imagine expecting to find toddlers in a nursery, but walking in to see fully grown adults. That's the kind of shock scientists felt. And the craziest part? The further back JWST looks, the more it finds galaxies breaking the rules. At this point, the word impossible is starting to sound less like science and more like an outdated label. The real plot twist started 2 years ago with the Hubble Space Telescope. In one of its deep space surveys, Hubble spotted an odd little speck of light at the very edge of the observable universe. At the time, scientists thought, that's interesting. Probably just a small, distant galaxy. They couldn't have been more wrong. When JWST turned its unmatched infrared eyes toward that speck, the image transformed. That tiny dot wasn't small at all. It was a monstrous primordial galaxy now known as GZ9P3. Located at a redshift of 9.3, we're seeing it as it was only 510 million years after the Big Bang. Yet it's already more massive than galaxies billions of years older. Something about its rapid growth defies the timelines we've held onto for decades, and we're just getting started with what this galaxy is hiding. Here's where G9P3 stops being just impressive and starts being downright baffling. This galaxy sits at a redshift of 9.3, meaning the light we're seeing left it only 510 million years after the Big Bang. In cosmic terms, that's practically the first heartbeat of the universe. And yet GZ9P3 is more massive than any other galaxy we've ever seen from this era. By all accounts, it shouldn't have had enough time to gather so many stars, so much gas, and such a dense structure. To reach its size this early, the stars inside it must have formed rapidly and efficiently, burning through gas clouds at a rate that blows past anything our models predict. If galaxies formed like this across the early universe, we'd have to throw out half of what we thought we knew about cosmic evolution. Think about it. A galaxy this large, this soon, is like finding a skyscraper in the middle of a Stone Age village. But it's not just the size of Gs 9P3 that has astronomers scratching their heads, it's the shape. When the JWST zoomed in, scientists noticed something unusual. Two bright patches within the galaxy's core. These aren't just random star clusters. They're dense nuclei, the gravitational hearts of galaxies, which means we're likely looking at two separate galaxies in the middle of a cosmic collision. That's wild because we're talking about a merger happening just 500 million years after the Big Bang. The universe at that time was still settling from its chaotic birth, yet here we have galaxies already smashing together and building bigger structures. If mergers like this were common back then, it could explain how early galaxies became massive so fast. They weren't growing alone, they were combining forces. And just when you think this galaxy can't get more surprising, it does. The JWST team didn't just measure its size and shape. They looked at the chemical fingerprints in its stars. What they found is a major twist. In the older stars of GZ9P3, they detected elements like silicon, carbon, and iron. Now here's the thing. Iron is the heaviest element stars can make before they explode as supernovae. When those stars die, they scatter these elements into space, enriching the cosmic gas. Finding these metals means that not only had stars already formed in GZ9P3, but many of them had already lived and died, spreading heavy elements far earlier than expected. Even more shocking, the galaxy contains more old stars than scientists predicted. This suggests that galaxies may have become chemically mature much faster than our models allow. If that's true, it means the early universe was a cosmic factory, pumping out and recycling stars at breakneck speed, a pace we've never accounted for. And here's the kicker. Discoveries like GZ9P3 don't just add a few footnotes to astronomy textbooks. They demand a whole new chapter. If galaxies this massive existed so soon after the Big Bang, then the standard models for galaxy growth are missing something big. One possibility? Galactic mergers played a far bigger role in the early universe than we realized. Instead of galaxies slowly growing over billions of years, they may have been crashing together almost immediately, pooling their stars, gas, and dark matter into gigantic systems. That would mean the early universe wasn't a calm, gradual builder of cosmic structures. It was a violent, high-speed construction zone. And if that's true, we'll have to rethink how stars formed, how quickly galaxies matured, and maybe even how the first cosmic structures came into being. But wait, GZ9P3 is just one crack in the wall. There's another, and it's known as the Hubble tension, and this one strikes at the heart of cosmology itself. Here's the deal. The Hubble constant measures the rate at which the universe is expanding. We have two main ways to calculate it. Method 1. Look at the cosmic microwave background, the leftover light from when the universe was only 380,000 years old. This gives one number for the expansion rate. Method 2. Use standard candles like supernovae, whose brightness we know. Compare how bright they should be to how bright they appear, and you get the expansion rate from a much later cosmic time. Sounds simple, right? Except the numbers don't match. The CMB method says the universe is expanding more slowly. The supernova method says it's expanding faster. This stubborn gap between the two, with no measurement errors to blame, is the Hubble tension. And it's a big reason scientists are starting to wonder if our entire cosmological model is incomplete. And just when you think one major tension is bad enough, another shows up. This one's called the S8 tension. S8 is a measure of how clumpy the matter in the universe is today, how much galaxies and dark matter have bunched together across space. Think of it like a cosmic jigsaw puzzle. S8 tells us how tightly the pieces are clustered. Now, there are two ways to measure this too. The first is by looking at low redshift observations, like weak gravitational lensing, which gives us a direct snapshot of the present-day universe. The second comes from the standard model of cosmology, which uses the CMB to predict how clumpy the universe should be now. And here's the twist. These two numbers don't match either. The CMB predicts a universe that's more clumpy than what we see. This mismatch is the S8 tension, and together with the Hubble tension, it's painting a picture of a universe that refuses to fit inside our neat theoretical box. To understand why this matters, you need to know how gravitational lensing works. Imagine a massive object, like a galaxy cluster, acting as a cosmic magnifying glass. Its gravity bends and distorts the light from even more distant galaxies behind it. By studying these distortions, astronomers can map where matter is, including dark matter we can't see, and figure out just how clumpy the universe is at different scales. These low redshift measurements are incredibly valuable because they give us a real-time look at the universe's structure, rather than relying only on ancient light from the CMB. But the fact that they don't match the predictions of our standard model, that's a sign that either we're missing a piece of physics or we're going to have to rewrite the rules entirely. Now here's where scientists rolled up their sleeves: the Flamingo simulation. This wasn't just any computer model. It was the largest cosmological simulation ever attempted. Flamingo tried to recreate the entire universe in a digital sandbox, including both dark matter, the invisible scaffolding that shapes galaxies, and baryonic matter, the normal atoms that make up stars, planets, and us. To pull this off, researchers used 30,000 computer processors running for a mind-bending 50 million CPU hours. That's like a single computer working non-stop for over 5,700 years. The goal? To see if adding more detailed physics into the mix, especially how normal matter interacts with dark matter, could finally explain the S8 tension. This was our best shot at bridging the gap between theory and observation. If Flamingo could replicate the universe we see today, maybe the tensions would disappear. But what it found only made things more puzzling. Here's the frustrating part. Even with all that computing power and precision, Flamingo's results still showed a universe more clumpy than what we observe. In other words, the simulation agreed with the predictions from the cosmic microwave background, not the low redshift gravitational lensing measurements. That means the S8 tension didn't shrink. It stayed just as strong. And this isn't just a JWST thing. Other powerful observatories are also reporting the same smoother, less clumpy universe. So either every telescope and lensing survey is missing something, or our standard cosmological model simply doesn't describe reality as well as we thought. If you were hoping JWST might settle the Hubble tension, think again. It's the opposite. One of JWST's early science goals was to measure the expansion rate of the universe using its incredible sensitivity and resolution. And when it did, it confirmed the same faster expansion rate that the Hubble Space Telescope had already measured using standard candles. That means the gap between the CMB-based prediction and the direct measurement isn't closing. It's getting harder to explain away. The more precise our instruments get, the more stubborn these tensions become, which leaves cosmologists with a big choice. Either there's something seriously wrong with our measurements, or the universe has been hiding some fundamental physics we've yet to uncover. At this point, most scientists agree, measurement errors aren't the culprit. We've cross-checked data from multiple telescopes, wavelengths, and methods. The numbers keep coming back the same, which means we're left with a much more unsettling possibility. Our understanding of the universe might be fundamentally wrong. If our standard cosmological model, the one that's been our best guide for decades, can't explain the Hubble and S8 tensions, then we may need to rewrite it. That could mean new forms of matter or energy, unknown forces, or physics that only appear at the largest cosmic scales. It's a daunting idea, but also an exciting one. And with cracks in the model, the wild theories are pouring in. Some researchers are suggesting we may need to remove dark matter entirely and replace it with alternative explanations for how galaxies form and move. Others are proposing entirely new cosmological models where the laws of physics themselves might have evolved, or where early dark energy briefly sped up the universe's expansion. A few even suggest our universe might be interacting with something beyond it, a multiverse perhaps, changing its behavior in ways we can't yet detect directly. The truth is, we're in uncharted territory, and GE 9P3 might just be the first of many discoveries forcing us to rethink reality from the ground up. JWST hasn't just found the oldest galaxy ever, it's rewriting the first chapters of our cosmic history. We might be standing at the edge of a scientific revolution. So, what's your theory? Drop it in the comments, and if you're ready for more, hit like, and subscribe.